Greetings, my calculus students. Today we will continue to be talking about differentiation. Section 3.2, Basic Differentiation Rules, Part 1. So, we're going to take a look at the derivative, but good news, we're not going to go through that whole big thing of the definition of the derivative today. Today I'm going to give you some shortcuts. But I think it's really important for you to remember that the derivative helps you to find the slope of the line at any given point. So let's consider the derivative of this function, f of x equals 5. So when we think of slope, we think of rise over run. So if you look at this horizontal line, you will see that there is no rise, but there is all of this run. So let's see here, what would the slope of that line be? Well, let's see here, the slope of this line is going to be equal to 0 because it's a horizontal line. So, since the slope of my line is equal to 0, the derivative of f of x in this particular problem would in fact be 0 because the slope is always 0 no matter where I'm at on the line. Right here the slope is 0, right here the slope is 0. Slope is always equal to 0. Now, as a matter of fact, this rule is actually true for any horizontal line. It gives us the rule, the derivative of any constant is equal to 0. No matter what that is, the derivative of any constant is equal to 0. All right, let's move on. So we're going to find the derivatives of all of these functions. Oh, man. That would be a pain to do if we had to do the definition of the derivative with every single one. But good news, all of these problems, every single one of them, works with one simple derivative rule. The derivative of x to the n is equal to n times x to the n minus 1. So let me show you what I mean by that, and we'll go through all of these problems. We'll go through all of these problems. So if you look here, this is really x to the first power. And according to my derivative rule, what I do is I take that x, that 1 that's up in the exponent, and I put it down in front of the number, and I reduce the exponent by 1. So my derivative in this problem would be 1 times x to the 0 power. X to the 0 power is equal to 1. So the derivative of x is just 1. What about the second one? F of x is equal to x squared. Well, according to my derivative rule, what I would do is I take that 2, I put it down front, and I reduce my exponent by 1. So f prime of x is equal to 2x to the first power. The next one. What about the next one? X to the third power. Well, again, we take that 3, we put it down front. 3 times x, and we reduce the exponent by 1, 3x squared. What about the next one? X to the fourth power. Okay, let's see here. We take the 4, we put it down front, we reduce our exponent by 1. Not bad. What about number 5 here? Roman numeral 5, v. What do we do here? That's not written in that form. I don't know what. Oh, man. Here's what you have to remember. You have to remember that x, the square root of x, is the same as x to the 1/2 power. And now my rule doesn't change at all. I still take that 1/2 in front, and I reduce my exponent by 1. 1/2 minus 1 is negative 1/2. To write that in a slightly different form, that would be 1 over 2 times the square root of x. That x to the negative 1/2 power would put it on the denominator of a fraction. What about Roman numeral 6? Again, we take that 3/2, we put it in front, we reduce our exponent by 1. What about Roman numeral 7? Ooh, okay. Well, again, you have to remember that that is x to the negative first power. So it's all about rewriting it. And then my derivative is easy. Just take that negative 1, put it in front of the x, and reduce the exponent by 1. What about Roman numeral 8? Remember that that's x to the negative second power. Same thing. We take that negative 2, we put it in front, and we reduce my exponent by 1. So the derivative of x to the negative second power is negative 2x to the negative third power. Finally, what about this guy? Okay, well, this is x to the negative 1/2 power. So the derivative is going to be negative 1/2 x, reduce the exponent by 1 to the negative 3/2 power. Folks, that derivative rule is very, very easy once you get the hang of it and practice that for a little bit. The calculus is easy. The difficult part will be maybe doing the algebraic manipulation or realizing what the problem actually is that you're working with. This makes problems like this one, find the equation of the tangent line, f of x equals x to the third power when x is equal to -2, a lot easier than what it was before. So just the first thing we need to do to find the equation of a line, when we're finding any equation of a line, we need a slope and a point. Okay, well, let's see here. Let's handle the point part first. We know that x is equal to -2. So the coordinate pair that I'm going to do is I'm going to take that -2, I'm going to plug it into my equation. And that'll give me -8. So the point that I have is going to be -2, -8. What about the slope part? Well, the slope part, we use the derivative. And we know the derivative of x to the third is going to be 3x squared. Again, we move that exponent down in front, reduce the exponent by 1. Okay, but now that gives me the rule for the for the slope at any point. The specific point I want is at -2. So I'm going to figure out what f prime of -2 is equal to. I'm going to plug that into my equation. Now remember, rules of exponents, we got to square that -2 first. And now we do the multiplication, so I end up with 12. So my equation, when it's all said and done, let's see here, y equals, or I'll use y minus y1 equals m times x minus x1. I'll use point slope form. So that'll give me y minus -8 equals 12 times x minus -2. Let's see here, that'll give me x plus 8 equals 12 times x plus 2, or 12x plus 24. Final answer will be 12x plus 16. Actually looks like, right? So I just did the problem and made sure you knew exactly what it looked like here. So the red line is, of course, x to the third power, and the blue line is that tangent line we just found. Cool deal. But what if we have a constant in front of a function? What happens then? What if it's 4x squared instead of just regular old plain x squared? Well, the good news is the calculus remains easy, right? We just are going to take the derivative of that x squared just like we did before, and then we'll multiply it by that constant that was in front. So c times f of x is the same, when we take the derivative of that, is c times f prime of x, where c is going to be the constant. So my problem here is no different than the ones I was actually just doing. The derivative, f prime of x, is equal to 4 times whatever the derivative of x squared was, which we know is just 2x. So my final answer for the derivative, f prime of x, equals 8x. Not bad. Let's take a look at a couple more examples. And again, with these problems, half the battle is going to be rewriting it in that form that we have that constant times the function. So here in A, for example, we would rewrite this as 4x to the -2nd power, right? That's the exact same thing. And then when I find the derivative, y prime, it's 4 times -2x to the -3rd power, right? That's the derivative of x to the -2nd power, which gives me -8x to the -3rd power. What about the second one? Again, change the form. Make it look like that constant times the function. So 2/3 times x to the 3rd power. My derivative, I'll write it as dy dx this time, is 2/3 times 3x squared. Or, final answer, 2x squared when I simplify it down. What about letter C? If we rewrite that, that would be 4x to the 1/2 power. Take the derivative, 4 times 1/2 x to the -1/2 power. Or, writing it in its different form, 2x to the -1/2 power. Or, if you're really feeling fancy, 2 over the square root of x. What about D? Rewrite that one as y equals 4 times x to the -2/3 power. That one was tricky, right? The third root would be on the denominator and the x squared. That's the exponent right there. When we take the derivative, y prime, it's 4 times -2/3 x, reduce that to the -5/3 power. Or -8/3 x to the -5/3 power. That one's kind of gross. The niceness and simplicity of calculus continues. If we have the sum or difference of multiple things, multiple little tiny functions, we can take the derivatives of each one of those parts individually. So for example, if we wanted to find the derivative of s of t, when s of t was equal to t to the third minus 4t squared plus 3t minus 5, we can just simply take the derivative of each one of these individual parts. Let's see what that looks like. S prime of t equals, the derivative of t to the third is 3t squared. Then we got this minus 4 times the derivative of t squared, which is 2t. The next part, plus 3t, the derivative of 3t is 3. And lastly, minus the derivative of 5, which is just 0. Simplify that down, we get s prime of t is equal to 3t squared minus 8t plus 3. Folks, the change in variable here doesn't mean anything different. T's, x's, y's, whatever. When we take the derivative with respect to it, we're just okay. Ew, but what about a quantity squared? Well, folks, there actually is, spoiler alert, there actually is a rule that would help us with this, and it's a little bit more complicated. It's not quite as nice and as simple as the other problems. So for right now, when you see a problem that looks like this, you're going to actually have to do some algebra up front. So you're going to have to take that 3x squared minus 5 squared and multiply by itself and actually multiply this out. Now, that'll involve me foiling, so that's 9x to the fourth. Minus 15x squared minus 15x squared with the outsides and the insides, plus 25. One more simplification before I take the derivative, because, folks, it's easier to simplify up front algebraically before you take the derivative. And then when you take the derivative, the math isn't all that difficult. So we got 9 times, let's see here, that would be 4x to the third minus 30 times 2x plus 0. Simplify it all down. I end up with 36x to the third power minus 60x. So not bad when you know the shortcuts. Certainly beats having to do that definition of the derivative all the time. Woohoo! Thank you, Mr. Huff, for the shortcut. No. Thank you, Isaac Newton. All right. Some homework problems. Try those out. If you need any help, please let me know. Good luck.